Good morning, ladies and gentlemen. My name is Lily Poulikakos from Empire, Switzerland. I am the chair of TC WMR, and together with my co-chair, Emiliano Pasquini from University of Padua, we're very glad to give you a summary of our activities in Rilem Technical Committee 279 WMR on valorization of waste and secondary materials for roads. Thank you very much for the invitation in this Rilem week in Vancouver in September of 2023. I will start by giving you some motivation about why we came up with this technical committee, this idea. Then I'll give you a summary of activities that we've had so far in this TC and some of the results. Of course, all of our most of our activities have already been published, and you're very welcome to access them and contact us if you have any questions. Also, I will show you some follow-up TCs that have already been approved for this TC. I would like to begin by giving you a motivation about why we came up with this TC. So the main motivation is to contribute to the circular economy, of course. So here we're talking about the choice of raw materials, but we want to be environmentally friendly in all aspects of our mixture. For example, when we prepare the mixture, during the construction phase, in the use phase, and the end of life. Waste is a very pressing problem right now. Here I'm showing you some numbers in Europe. These waste materials were chosen because of their possibility to be used as alternative materials for roads. You see on the left-hand side some of these waste materials. You see the source of these materials. You see the generated amounts, and you see also the available amounts. If we take, for example, concrete, that is the most generated waste material. It comes from construction and demolition waste. In Europe, about 350 million tons are produced every year, and still more than 260 million tons are available. The rest is recycled or reused. There are also other types of materials. Again, the available amounts are in the millions of tons. So waste is not limited to Europe. There is a substantial problem worldwide, and many countries are trying to do something about it. If you visit any of the recycling plants, like we have done here in Switzerland, we visited a polyethylene recycling plant. Here you see the mountains of waste, and it becomes more of a pressing issue when you see this. In 2017, we published a review paper about using waste, and this paper was chosen by the European Commission for their Science for the Environment policy publication. What we learned from this paper was that there are some materials, some waste materials that could be options for roads. They should be exploited further. We looked at various scenarios. We looked at the life cycle assessment, life cycle cost assessment, and we saw that it's possible to save in cost, CO2, and energy consumption. However, the technical readiness level for these materials were not the same. It varied amongst materials and in different geographic locations. So what we saw is that it's very important to have all the stakeholders involved. We have to have access to knowledge on how to use such materials. The technology might vary. And our community, the scientific community, can make a more significant effort to bring this kind of knowledge to the practicing professionals. And that's where Rilem plays a very important role. Also, we need legislation and standards for use of such materials. Coming back to the technology readiness level, or TRL, it's a scale that was developed by NASA to evaluate the various types of technologies. So, in terms of our materials, you see, for example, that chrome rubber using the wet process has a very high TRL. We estimated it to be from 7 to 9, whereas, for example, recycled glass has a much lower TRL. We estimate it to be about 4. And while because its use is primarily at the laboratory scale. You can find the whole analysis in the paper that is referenced below. In this TC, we have used various types of materials that you see pointed out. We have also looked at the performance of these alternative materials as documented in the literature, and we looked at rotting, moisture resistance, stiffness, and fatigue, and you see that there are various type of waste materials that performed very similar to all virgin materials. So it seems that the information that's out there shows that it's possible to use such material. Therefore, we put together a technical committee in 2017. It's been active since 2017. And we've had Bernard Hofgo from TU Vienna, who was our deputy chair until 2019. And as I mentioned, Emiliano Pasquini from University of Padua has been the deputy chair since 2019. We started in 2017 and we've been active for 5 years. We have had more than 100 members. It shows that this topic is of interest for our community. And we've had many active members. So not all the 100 are active, but many have been active. What we have done in this TC is to combine a literature review with experimental work. We wrote very detailed test protocols, and we also wrote a state-of-the-art report that was just published. We have published various papers in scientific journals, and we are in the process of producing recommendations. Some recommendations have already been published in the STAR report. We had a workshop halfway in the conference in Lyon, and we also had a second workshop at the end of the TC on June of 2023 at the European Asphalt Technology Association conference in Poland. We had designed 5 technical groups. Technical group 1 was on waste plastic modified asphalt binders. The leader was Marianne Tushar from ZAG. TG2 was on chrome rubber modified asphalt binders. The leader was George Pace from University of Minho. TG3 on waste aggregates in asphalt mixtures was led by Fernando Moreno, University of Granada, Augusto Canone Falchetto from the University of Alto, Emiliano Pasquini from the University of Padua. TG4 on environmental risk assessment was led by Umaya Marciuk from Kerema, Gaetano Di Minho from University of Palermo. However, this TG was unfortunately not active through the life of RTC. And TG5 on life cycle assessment was led by Davide Lopresti from University of Palermo, Ana Jimenez del Barco Carrion from University of Granada. We were able to conduct various meetings every year since 2017. Also during COVID 2020, 2021, we were able to have various virtual meetings, and actually the TC remained very active. Our first workshop was in Lyon in 2020. This was online. We reported on our TG activities, and we also had invited 2 external relevant reviewers. We had more than 70 participants online. Our end of TC event was on 15th of June 2023, just this year, right after the European Asphalt Technology Association in Gdansk, Poland. Again, we reported on our TC activities, various TGs reported, and we had 2 external presenters. We were also invited to participate online at the ICPT conference in Beijing. We invited again 2 external reviewers, and we reported on our various TG activities. I would like to continue by summarizing some of our outputs. As I mentioned, our papers have already been published, and many of the information that I present to you here are either in the papers that are referenced on the slides or in our STAR report. I would like to give you an example about the TG1 activities where we looked at waste plastic modified asphalt binders. Here we had 11 labs participating using 2 types of polyethylene. These polyethylenes were from the recycling plant that I just showed you in Switzerland, so we shipped the waste materials to all of our partners. And here, this example shows you the round robin results showing modulus compared to the temperature. And you see that when we look at lower temperatures, up to about 40 degrees, the results of the different labs coincide. However, once we go above 40 degrees, the results seem to diverge. And although we have used the same grade of binder and the same type of PE, here we're talking about a waste material that is inherently not homogeneous. And once we are at colder temperatures, the whole blend behaves elastically. But once we go above this 40 degrees, then we have elastic material, the PE, that is in a viscoelastic material. So our binder starts to become softer, whereas the polyethylene remains elastic. And so the difference shows up a lot more. An example of the work of TG2 on chrome rubber modified asphalt binders is shown here. In this case, we had 4 labs involved and 4 types of chrome rubber were looked at. Again, you'll see a complex modulus values for different binders, the 7100 binder and 7100 binder blended with 3 types of rubber and 2 mounts of rubber. And in most cases, you see that there is a reduction of the complex modulus with the addition of chrome rubber. And as is seen here, the type and the amount has an effect on the complex modulus. TG3 involved waste aggregates in asphalt mixtures. In this case, we had 8 labs that participated using 4 materials. The materials were steel slag, recycled concrete aggregates, construction demolition waste, and chrome rubber. We see here in this table some of the results. In most cases, the mixtures that were prepared with waste materials had a higher binder content. So you see the optimum binder content is listed here. We were able to reach the volumetric properties that was required, and also the mechanical properties were completely acceptable, as you see in the Marshall strength in this table. TG3 and TG1 combined forces in looking at polyethylene blended with mixtures. In this case, an asphalt concrete with a maximum aggregate size of 16 millimeters was investigated using all local materials except for the plastic waste that was sent to them from Switzerland. This mixture also had a void content of about 4%. So this example that I'm showing you here is looking at the indirect tensile strength in comparison to the reference strength in dry state. And you see this ratio as a function of the amount of polyethylene. And you see as the amount of polyethylene is increasing, it seems like the strength is increasing in comparison to the reference. TG5 looked at life cycle assessment. In this case, there were 7 participating labs. They developed benchmark values. They looked at the material from cradle to gate, and that means that the performance of these materials were not considered in their analysis. What they have seen is asphalt concrete has about 60 kilograms of CO2 per ton. And SMA, which is the stone mastic asphalt, has more CO2, about 75 kilograms of CO2 per ton. They have also seen that climate change seems to be linked to the transport phase of the material, whereas energy consumption is linked more to the material supply and the mix design. So in other words, bitumen content. For selected studies, they have looked at the WMR mixtures that we have used in TG3, and they saw that the stone mastic asphalt and the semi-dense asphalt were more environmentally friendly when WMR mixtures were used in terms of climate change and energy use. However, for asphalt concrete dense mixtures, that was not always clear. And so this work will go on, and they have recommended to do more studies to look at these aspects more. I would like to summarize our findings now for you. What we have seen through our work is that we really need to come up with appropriate testing procedures. When we have alternative materials, we might have certain susceptibilities. For example, susceptibility to cracking or rotting or certain types of failures. So we have to make sure that we test for those types of failures. Otherwise, we might not catch that. We have seen also that traditional test methods might not be appropriate when we have waste in the materials. In case of plastic or rubber, for example, the softening point temperature, we got very funny results there. And when we used also microscopy techniques, and through those techniques, we could see that the plastics or the rubbers are still existing as elastic bodies within our mixture. So as our material becomes softer with temperature, then these elastic bodies help in performance of the material. I also showed you some examples when the degree of repeatability and reproducibility could be reduced as we're working with waste materials. They are not inherently homogeneous, therefore they introduce more inhomogeneity in our mixtures and blends. We have seen then, I hope that I was able to convince you that we can see similar performance as the reference mixtures as long as the mix designs are adjusted. For example, in some cases, we had to increase the binder content. So mechanical performance can be achieved. However, does it really make sense to use such materials? And in that case, we really need to look at environmental aspects such as leaching and life cycle assessment that looks like the material in its whole life cycle. As I mentioned, our various TGs have had several publications. You're very welcome to access them, and if you have any questions, feel free to call us. And we also had 3 workshops, as I summarized earlier. We also presented at the PhD schools twice. And the state of the art report was just published, and our recommendations are currently under preparation. Here is the state of the art report that was just published. I'm very happy to report that the work of the TC continues. There are two follow-up TCs that have already been approved. Actually, at the Rilem week, they were approved. The first one is called Design and Performance of Alternative Materials. It is chaired by Augusto Carone Falchetto, and the deputy chair is Fan Yin. The second TC is Sustainability of Alternative Paving Materials. It's chaired by Davide Lopresti, and the deputy chair is Emmanuel Chaillot. Invite you to contact the chairs or deputy chairs if you're interested in this type of activity. At this point, I would like to acknowledge the tremendous work that was done by all of our technical group leaders that you see here, as well as all of our active members and their organizations that have supported all the activities in this TC. And I thank you all for your attention.